Welcome to the Space Telescope Public Lecture Series. Tonight's lecture, Eta Carinae and the Homunculus Nebula in 3D by Frank Summers of the Space Telescope Science Institute. I am your host, also known as Frank Summers of the Space Telescope Science Institute. I work in the Office of Public Outreach, and it is my pleasure to be your host here each and every month. It is also my pleasure to thank our amazing tech team, Thomas Marufu and Grant Justice, who take care of recording this and getting it out to YouTube. Our upcoming talks on June 7th, Understanding the Formation and Evolution of Galaxies by Cameron Hummels of Caltech. And Cameron is a fantastic guy. I'm really looking forward to seeing what he has for us next month. In July, it is an unscheduled talk because I was sort of keeping July open for the James Webb Space Telescope, but they've pushed to August, so now July is open. But I guarantee you we will have a fascinating topic with an amazing speaker on July 5th. On August 2nd, that's when we will hear the first results from the Webb Space Telescope. And the Webb Mission Office has promised me a wonderful speaker. They just haven't said who yet. So I know you're all looking forward to it. August 2nd, the Public Lecture Series will talk about the first results from Webb. To follow this, go to our website, www.stsci.edu/public-lectures. You will find this page here and links to the webcast on the left-hand side of the page and the subscribe button for our email on the right-hand side of the page, okay? Also, we will have, of course, lists of the upcoming lectures. And if you click on each one of those lectures, all the details of that lecture appear, including the description. And after it's been recorded, links to both the STSCI webcast and the recording on YouTube. If you would like our announcements, as I showed you, it's very easy just to enter your email address, push the button, and sign up on our website. You can also just subscribe to our YouTube channel. This is youtube.com, Hubble Space Telescope, all one word. You will get notices of new videos and reminders of live events like the one you're watching right now. If you have comments or questions, you can send them to us at publiclecture@stsci.edu. Our social media for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute is available on Facebook, Twitter, YouTube, and Instagram. I myself, as your host, only do a small amount of social media, and you can find me on Facebook and Twitter as Dr. Frank Summers. And now our news from the universe for May 2022. And as we've done every month since it launched, we're giving you another Webb update. Alignment check? Check. All right. So the Webb Space Telescope was launched in December, and it reached L2. It orbited around the L2 point in January. And since that time, we've been updating you on how they've been aligning the mirrors. And I don't know if Quen showed this last month, but this was the latest thing that we had shown before this month. And this is the Webb NIRCam alignment image. So NIRCam is the near infrared camera. It's kind of going to be the workhorse camera of Webb in producing images. And it was the first to be aligned. And look at this gorgeous star. And as we've discussed, it has a 6-pointed star, along with, two extra little point struts that come out the center. So this is the PSF, the point spread function for the Webb Space Telescope. And it's just like absolutely clean and gorgeous. But NIRCam is only one of the instruments on Webb. And here is the focal plane and all of the instruments out there. So NIRCam is here in the center. On the up left is NIRSpec, the near and infrared spectrometer. Down here is the FGS, the fine guidance sensor. This one is NIRIS, um, the near infrared imager and slitless spectroscopy. And in the upper right, we have MIRI, the mid-infrared instrument. So there are 5 major instruments on Webb, and all of them can be used for science. So after aligning NIRCam, they went on to align all of the other instruments, and they took observations of the same field at different times, of course, because they were using different they sent the light to different instruments, and they checked it out. And so here is what they call the Webb Telescope Image Sharpness Check. And look at this. This is all 5 instruments beautifully aligned, okay? And you can't really tell from here, so they added another version of this with some details, all right? And there you can see those beautiful 6-pointed stars over in NIRISS and in the FGS and in NIRSpec, as well as what we saw from NIRCam last month, and all the way up there on right in MIRI as well. So this is really cool. And one of the things that reminds me is that for a lot of the near infrared, a good amount of what you're going to see is stars, because the gas in the infrared doesn't show up until about 4 microns. And MIRI starts at 5 microns. So MIRI's where we're going to get most of the gas. NIRCam, NIRISS, and such will have some gas in it, but it's going to be an awful lot of stars, an awful lot of really beautiful, gorgeous 6-pointed stars. And so the natural question we have when you look at something like this is, okay, this is really great, but how does this actually compare to previous space telescopes? And of course, we weren't the only ones who thought about this. Andreas Gaspar actually went out and found observations of that same field with previous telescopes. So what you see on the left is the WISE space telescope at 4.6 microns. Then you have the Spitzer Space Telescope at 8.6 microns. Spitzer was the great observatory that was retired a little over a year ago. And then you have the observation from MIRI at 7.7 microns. So these are roughly comparing apples to apples here. And you'll see just how much more detail MIRI has than Spitzer, and so much more than WISE itself. So yes, this is a quantum leap in infrared astronomy being done with the Webb Space Telescope, and we're all just chomping on the bit for those first images. How long is that going to take? Well, here is the chart I showed you several months ago about Webb's commissioning. We arrived at L2 about 30 days after launch, and this green stuff here, all right, all of this green stuff around here is the instrument focusing and alignment. So we have now gotten to the end of the green stuff, okay? And there are only a couple more months, and this is the science instrument commissioning phase. We have moved out of the alignment and getting things set, and now we start the science instrument commissioning phase. And that's really exciting because, you know, we are 3 months at most away from seeing these amazing images from the Webb Space Telescope. That's all I have for the news from the universe. It's time to move on to our featured talk. And our speaker tonight is me. Many of you know me because I've been doing this for almost 20 years now. Let's see, it will be 20 years in June. In June of this year, it'll be 20 years that I have been hosting the public lecture series. So a lot of you know my resume, some of you don't. And so let me just give you the basics. I did my undergraduate degree at Virginia Tech and my graduate degree in astronomy at the University of California, Berkeley. I then went on and did postdocs at Princeton University and Columbia University before switching from research-oriented to outreach-oriented. You see, because Neil Tyson was in the office next to me at Princeton, and he hired me to start working on the rebuilding of the Hayden Planetarium. That turned into the complete demolition of the Hayden Planetarium and rebuilding it up as the Rose Center for Earth and Space. And that took about 5 years that I was in New York City. Then I moved out of New York City, came down to Baltimore, where I've been working on the Hubble project ever since. I always like to share one interesting tidbit about myself, and I can't really remember what interesting tidbits I've shared previously. So today I'll just tell you that I met my wife at the Ballroom Dance Club at the University of California, Berkeley. Go Bears. Turns out there was a good number of physicists and astronomers and other technical types who took ballroom dancing. And the ballroom dancing was quite the social club. I know of at least 3 marriages that came out of the University of California Ballroom Dance Club. Mine, fortunately, was one of them. All right, so ladies and gentlemen, Dr. Frank Summers. All right. Now that I've introduced myself, let's start my talk. I'm going to talk to you tonight about Eta Carinae and the Homunculus Nebula in 3D. And I am not an expert in Eta Carinae, okay? I'm a visualizer. I call myself an astrophysicist. But in order to do any visualization, I need to do a lot of homework, read a lot of scientific papers, and study other people's research. And I'm going to give you some of the feel of that as we tell the story of Eta Car. And we're going to start by talking about the brightest star in the night sky. And as many of you know, it is, as shown here, Sirius, which is in the constellation of Canis Major. That is right next to the constellation of Orion, because Canis Major is one of the hunting dogs of Orion, and Orion has its famous stars of Betelgeuse and Rigel. And it also has the small dog, Canis Minor, and its bright star Procyon. So Sirius, the brightest star in the night sky, is in a very interesting region of the sky. But there's also a very interesting region around the second brightest star in the night sky. Have you ever thought what that one is? Most people don't really know it, but I will tell you, it is the star Canopus. And this is a wonderful image from Akira Fujii, having both Sirius and Canopus and a huge swath of the sky. I love these wide field images. Canopus is part of the ancient constellation called Argo Navis. All right, now you may not have heard of that because we no longer recognize it, okay? It was a constellation that people thought about in the old days. It's this giant ship. It's actually the ship of the Argonauts. And you can see it covers a huge swath of the sky. So astronomers decided to change things around and break up Argo Navis into 3 separate constellations, that is shown here as Carina, the keel of the ship, Vela, the sails of the ship, and Puppis, the poop deck. So if you're like me and you live in the Northern Hemisphere, well, you probably haven't seen these constellations. As a matter of fact, I only got to see this region of the sky once in my life when I was invited down to Brazil to give a talk. And also in that talk, also on the program of that conference was the wonderful astrophotographer Tunç Tezel, he's from Turkey. And he invited me to go out and do some astrophotography with him one night during the conference. And on the right, you can see an amazing image where you've got the galactic center and this wonderful stretch of really interesting sky, really nice and high. And we don't get that in the Northern Hemisphere. You only get that in the Southern Hemisphere, where you really get the Milky Way up nice and high. And I have proof that I was there, because if you look right here, that's me. Tunç did a wonderful thing where he took a portrait of me with the galactic sky, and that is something that I treasure because it was just such an amazing experience to be out with him. But let's take a look at this region. We have Canopus here on the right, and all the way over on the left, we have Alpha Centauri, which is the nearest bright star to the sun. Alpha Centauri is the same spectral type as the sun, and it's only like 4 1/3 light years away. There's actually one star that's even closer, Proxima Centauri, but that's a really faint little red star. So Alpha Centauri is the one you can look at. If you come next to Alpha Centauri is the Southern Cross, the constellation called Crux. And across from that is something that we call the False Cross. The False Cross is stars in Carina and Vela, but they also have that cross pattern. And actually, when I was there looking at it, I got the two confused, and it took me a while to really recognize, okay, there's the cross and there's the false cross. And right in between these two is our destination, and that is the Carina Nebula, okay? So the Carina Nebula is an amazing place, and I'm going to back off just a little bit to show you where it's located in the galaxy. So on an all sky of the galaxy, you can see that the galactic center is in here, and the Carina Nebula is over here, all right? So it's in the direction of the galactic center, but it's not against all that light of the galactic center and the bulge, so it's far enough away that we can look at it in detail without too much background confusion. And if you look at the plan view of the galaxy, looking down onto it, this is a drawing by Robert Hurt. This drawing is oriented such that the sun is here. And let's zoom in on that. And with the sun here, the Carina Nebula is over here in the next spiral arm over. This is the Sagittarius spiral arm. So the Carina Nebula is only about 7,500 light years away, which, you know, sounds big, but it's actually really close when you're talking about these giant star forming regions. So it's a really good view of the Carina Nebula from our sun. This is the Carina Nebula from the Digitized Sky Survey. It contains thousands of stars, and one researcher described it as the most amazing place for studying high mass stars, that there are more high mass stars of interest that you can study in detail than any other place. We zoom in a little bit closer. This is a really, really high resolution image from the Very Large Telescope, the VLT. And you can see that it alternates between these bright areas where you've got newly formed stars or stars that are forming, and these dark lanes of dust that are on the foreground, sort of blocking our view. So there's a lot of star formation, there's dust that's collapsing, and there's a lot of interesting things going on here. Hubble has a very famous montage, a mosaic image, one of the largest mosaics Hubble's ever done in this region. And we zoom into that, and you can see there's just a ton of things happening here, the stars and the gas and the dust. And matter of fact, there are at least 3 Hubble press release images that have come from this region. So this one big image was a release, but also these here, the dark pillars down here, the light and shadow image up here, and one of my favorites, the Mystic Mountain image over here. Really cool stuff. All right, but what I want to talk about shows up really good in optical, but shows up even better when we go to the infrared. This is the infrared view of the Carina Nebula from the Spitzer Space Telescope. And when I remove that Hubble overlay, you can see a honking bright star. That's a honking bright thing, and that is our final destination. That is Eta Carinae. All right, Eta Carinae is the brightest object on the night sky in infrared wavelengths. All right, so, you know, if you think about, you know, Sirius being the brightest star in the night sky, invisible, Eta Car is the brightest in infrared. And we zoom in a little bit, and you can see the effect that Eta Car has had on the gas and dust in the Carina Nebula. You can see that it's evacuated this big cavity around it with its strong radiation and strong stellar winds. You can also see these pillars down here that are all pointing toward it, which shows that the wind from Eta Car blowing out across the nebula, creating these pillars that point back toward the source. So Eta Car is really something special in infrared. However, that's not what it's actually particularly known for. It's actually known for something called the Great Eruption, and that occurred invisible. So this is the light curve of Eta Car from 1800 to today. And you can see around 1840s, 1835 to 1855, there was a jump in its light. This is what's called the Great Eruption, all right? And it brightened, and it became temporarily brighter than Canopus. So for a very short time, it was the second brightest star in the night sky in visible light. But then over the next ensuing decades, it slowly faded away, all right, until the late 1800s. Then it underwent a small brightening and decrease, which researchers have taken to calling the Lesser Eruption. So in the 1890s, Eta Car had another eruption, but then again, it faded away. It stayed down for a few decades, but in around the 1930s, 1940s, it had a fast rise, and it continued to slowly rise across the 20th century. So this is really, really unusual, especially when you consider the difference between getting up to, -1 magnitude and all the way down to, 8 or 9th magnitude. And 5 orders of magnitude is a factor of 100 in brightness, okay? So this is almost a factor of 10,000 in brightness, certainly about at least a factor of 3,000 in brightness between its peak and its trough down here. So this is one of the things that makes it being called a supernova impostor, because of this massive brightening. Now, just to make sure you remember what a supernova is, this is images from David Malin of supernova 1987A. And on the left is the before image, and on the right is the after image. The supernova is an incredible brightening. However, the star that went supernova here to make 87A no longer exists because it exploded, it blew itself up, its guts are streaming across interstellar space right now. Eta Car, on the other hand, did not go away. It survived this massive brightening, this eruption, and still is coming back, and is rising and may even get back up to its previous brightness in a few decades. So because it had a supernova-like brightening, but it survived, that's hence it comes with the name a supernova impostor. So that's what Eta Car is really known for. And when we look at it today, what do we see? We see the Homunculus Nebula. Yeah, this is really cool. All right, the star is down deep in here, but it's actually behind it's buried inside the Homunculus Nebula, and we can't really see the star. We can see some of the light from the star, but we don't see the star itself. All right, the Homunculus Nebula is a cloud of gas and dust that is blocking the light of the of Eta Car, and you can see that its shape is here. Is that it's got bipolar lobes, is what we describe it in thing. Basically, think of it as an hourglass. There's a bubble coming toward us. There's a bubble going away from us. It also has what I call equatorial emission. So stuff at the center of it, there's stuff spewing out along the equatorial plane. And so this is really kind of interesting that there's this nebula, and Hubble has observed this nebula over its lifetime. And we'll start with the 1995 image and then watch the nebula because it's going to grow. Here it is in 2008. And here it is in 2018. Yeah, we're watching it grow. And you might say, oh, well, you're just aligning the image. No, no. Take a look at these stars here, okay? I'll go back. 2008, 1995. One more time. Grow, grow, shrink, shrink. Yeah, we are seeing this nebula grow on human timescales. That usually doesn't happen, okay? And then if you trace that back to when it started, well, of course, that is the time of the Great Eruption. This nebula has been growing for about 180 years, since the 1840s. That's when the Homunculus Nebula was launched and exploded. So this Great Eruption produced this Homunculus Nebula. So let's go back to that light curve and try and understand it now that we know that the Homunculus Nebula is there. So in the 1840s, it had the eruption and it started launching this nebula. When the nebula was small, it was dense and it blocked the light of the star, and therefore the light of the star faded away. Then as the nebula gets larger and larger, well, you can start to see through it a little bit. It becomes less and less dense. You can start to see through it. And then the light of Eta Car starts coming through, and the visible light starts to rise over the 20th century. So the Homunculus Nebula explains the light curve, the strange light curve of Eta Car. But what about this thing, this lesser eruption? Did that also produce something? Well, we can't see, because we can't see through the Homunculus Nebula enough to actually see it, at least with visible light. But we can use spectroscopy to measure the velocity. And this paper used a spectroscopy to measure the velocity of a molecular hydrogen deep inside the Homunculus Nebula. And found, and these velocity diagrams here are difficult to understand, so I'm not going to try and explain them. But what they tell us is that there is a little Homunculus Nebula here, and its shape in terms of a bipolar structure and its orientation along these diagonals are the same as the Homunculus Nebula. The expansion time of this is actually is consistent with the eruption from the 1890s. It actually, if you work it back, it goes to about 1920. But this little Homunculus Nebula material probably got pushed by the radiation pressure or stellar winds from the star, which would speed it up. Okay, and so actually it would have, it's consistent with having been launched in the lesser eruption of the 1890s. The other thing that knowing that the Homunculus Nebula does is it explains why Eta Car is so bright in the infrared. So that gas and dust of the Homunculus Nebula block the light of the star, and these massive stars, which Eta Car is a very massive star, produce copious amounts of energetic light, which is absorbed by the Homunculus Nebula and the gas and the dust inside it, and re-radiated at infrared wavelengths. So the reason why most massive stars aren't this really bright in the infrared, but this one is so bright because the light is being reprocessed by the gas and dust within and along the surface, along the outer parts of the Homunculus Nebula. Infrared is, of course, not the only wavelength we can use to explore it. We have done multi-wavelength observations of the homunculus and the gas and dust around it. And here we have a press release image that includes visible, ultraviolet, hydrogen alpha, and X-ray. And let me tell you a couple of things we learned from those. If we look in ultraviolet light, these massive stars produce tremendous amounts of ultraviolet light. What we see is sort of some spiky emission through the tops of the lobes. There's spikes that come out. So it appears that it shows that the Homunculus Nebula has become a bit porous, and some of the light can escape from the star out through the top of the lobes. We also see this equatorial emission. These are spikes that come out from the center, and they match up with the equatorial emission that we saw in visible light. In hydrogen alpha, this is a gas that's about 3,000 degrees. Well, this image is sort of processed just to make the press release image, but I want to show you one that's a little oversaturated, so you can see the details of this hydrogen alpha emission, because there's a lot of cool stuff going on in here. And the first thing that I noticed is that, well, you've got this hydrogen alpha here that's been energized by the ultraviolet equatorial emission, both here and up here. All right, that you definitely see that the UV is heating this gas and causing it to glow. But there's a lot of other stuff that's not associated with that. And so what is that stuff doing? All right, and so there's a paper here that looked at the proper motion study of these knots out here. Where did all this hydrogen alpha gas come from? And so they looked at the gas that's glowing in hydrogen alpha and nitrogen emission, and they studied 800 of these little knots of gas using the 21 years of HST observations. So you can follow, 21 years apart is enough for them to actually move. You can measure their proper motion and then deduce a velocity. And the first thing you notice is that all of these vectors, all of these arrows are pointing away from Eta Car. So this stuff definitely came from Eta Car. It's flowing away. And if you work back when that stuff started flowing away, well, the red stuff, all these red arrows, they come from the Great Eruption around 1840. The green arrows, the stuff down here and the stuff up here, those green arrows roughly come from around 1550. And the blue stuff that's over here on the left side, that stuff mainly comes from around 1250. So this is evidence that Eta Car has not just had the Great Eruption, not just had the lesser eruption, but has had at least 2 other significant eruptions in the last 1,000 years. So this is a really, this is a star that's going to have multiple outbursts. And one of the things you notice is that the blue stuff is all one-sided. I mean, there's no blue stuff over here on the right, okay? And the green stuff seems to go up and down, but not really left and right. So there are different symmetries. So these outbursts that occurred roughly 300 years apart appear to have different symmetries. If we go on to the X-rays, the first thing I need to tell you is that there's a lot of these small little dots that are not actually part of Eta Car emission, okay? In X-rays, we can see X-ray binaries and galaxy point sources. So these are all, a lot of those are just background sources. It's mostly the cloudy stuff here that is the stuff that comes from around Eta Car. And my first question on this was, why are the X-rays on the outside? I mean, because if X-rays are the highest energy component that we're looking at here, and the energy source is deep down in the core, right? And so you'd expect the high energy stuff to be deep down in the core, right next to the energy source. But here we've got the highest energy stuff way on the outside. And that had me scratching my head until I went and did some reading some papers and understanding. Right? And so the explanation for why the X-rays are out on the edge is due to shock heating. It must be shock heating, that there's fast ejecta moving out, smashing into existing clouds and causing them to glow in X-rays. Okay, a low density, fast moving ejecta that's creating these high energy emission. And so we go back to that proper motion study that I just talked about. And here we have those same vectors that were deduced for the hydrogen alpha material, but overlaid on top of the X-ray image. So the X-ray, so we're trying to find out when this fast moving ejecta was launched. And if you look at it, you can see the blue stuff. Well, that's generally outside of the X-ray glow. It could be some of the blue stuff that's being ran into, but it's not the source of the fast-moving ejecta that's causing the X-rays. Same sort of thing for the stuff from 1550. This green stuff up here, that's outside of the X-ray emission. And this green stuff down here, well, that's actually in a hole of the X-ray emission. There's no real X-rays being emitted down here, so they don't seem correlated. So the conclusion is that this fast-moving ejecta should have come from the Great Eruption in the 1840s. That also fits with the fact that the orientation, this the elliptical axis of this is the same as the axis of the Homunculus Nebula. So there's the same sort of shape or orientation to the X-rays as the Homunculus. The problem is that the fast ejecta that would have come from the Great Eruption is not observed. In this study, they were looking for a material that's moving about 1,000 kilometers a second. And in order to create these X-rays, the fast-moving stuff had to be moving about 3,000 kilometers per second. If you do the energetics, that's how fast they need to be moving in order to excite these X-rays. And so they could not see that with this study. So there is more research to be done, but the conclusion of this study is that there is a high-energy, fast-moving component to the Great Eruption that we haven't seen, but that is what's causing these X-rays and the X-ray emission when it plows into pre-existing clouds and creates the X-ray emission. So here is the composite of it, where we've got the X-rays on the outside, you've got the hydrogen alpha here, you've got the ultraviolet here, and you've got the visible light here. And I will note that you can see the interaction between the ultraviolet hitting the hydrogen alpha here, and then again up in here, which is really kind of cool, you know, see the connections between these things. And this is really a lot of interesting structure. And you might ask yourself, can one star really do all this? The answer is no. One star can't do it. But two stars, well, that's what we think is going on. Because when you go in and investigate the Eta Car system, you find that it is a double star system with one really huge star of about 100 solar masses, and one large star about 30 solar masses. Both of these are really, really big stars, okay? But they're in a binary system. And here is the orbit on the right-hand side. That's a very elongated orbit, but it only takes 5.5 years for them to make their orbit. So we think of the small star orbiting around the big star, and every 5.5 years, it comes in past it. Now, this is what they call a colliding wind binary, because these massive stars have giant stellar winds. They produce incredible stellar winds. You saw how Eta Car's stellar wind streamed across the Carinae Nebula and created those pillars. Well, that 30 solar mass star also has a very strong solar wind, okay? And when it is at apastron, which means the farthest point in the orbit, the winds they interact a little bit, but not much. But bring that star in close to periastron, the closest point in their orbits, and then those winds interact strongly, and they will produce X-rays. And we have evidence of all this in one of the most gorgeous plots I've seen in a long time. This is the X-ray light curve of Eta Car. So using several different X-ray instruments, you can see over every 5.5 years, there's a giant peak in the X-ray emission from Eta Car as these two stars come in close together. The winds collide, they produce copious X-rays, and you've got this, this big emission. So this is what's going on in the core. You've got a colliding wind binary system that is the genesis of all of this stuff. So you then ask yourself, all right, well, this is a great eruption, and really, how did it happen? Okay. So first of all, let me just talk to you about why it's a great eruption. Okay. Eta Car A, the large star, lost about 10% of its mass. Okay. 10% of the star blow out. That's 10 to 20 solar masses blowing out in one event. That's a huge event. The total energy in the radiation from it, as well as the kinetic energy of the material flowing out, is about 10% of a supernova explosion. A supernova explosion, blows a star apart. It uses about 10 to the 51 ergs. This one, if you add everything together, it's about 10 to the 50th ergs of that. So this is a credible amount of energy. And also, when you look at the energetics, you sort of get violations of what's called the Eddington limit. I don't want to go into too much detail here, but if you use physics to figure out what is the maximum amount of energy that a star can release, okay, using basic physics of radiation and pressure and such, you get something called the Eddington limit. And the energetics of this great eruption kind of look like they violate the Eddington limit. And if it gets super Eddington luminosity here, you got to figure out why. And there's got to be a reason why. It really can't violate the Eddington limit because that's due to physics. But there's an awful, depending upon what you think is the mechanism, it sort of does violate the Eddington limit. So this is what makes it really great. So you got to consider the physics that's going on here, okay? You've got two very massive stars, okay? And down in their cores, they have nuclear fusion that's providing the energy that's powering these stars. And the nuclear fusion is going on at a prodigious rate. That energy that's created in the core goes out through the star in various ways, conduction, convection, and radiation. And the convective layers are this overturning of material. Hot material rises, cool material goes down. This overturning in these convective zones that can be quite violent and a little bit unstable. Then when you get out to the photosphere, you release all this radiation that actually has pressure associated. Radiation pressure can push things, can push gas clouds and everything. And then, of course, you've got stellar winds, which these are the charged particles streaming away from the stars at amazing rates for these massive stars. So those are the physics involved. And there are several hypotheses as to what caused the Great Eruption. Yeah, these are just hypotheses because we do not know which one is correct or if any of them are correct. All right. So it basically involves variations of all the physics. Okay. Radiation pressure and dynamical instabilities. So the dynamical instability is probably due to the convective things, and the radiation pressure end up pushing the outer layers of the star off. Or they could be gravity mode instabilities. And I will be honest with you, I did not truly understand what's going on here in this description. So I'm just going to leave it that there are some gravitational fluctuations that can go unstable and help cause the outer layers to go off. Another hypothesis I read about was a scaled down supernova explosion. So this must involve something of the nuclear fusion that's going on inside the star. And the explosion only goes so far, blows off the outer layers, but doesn't blow the star apart. And finally, one of the more inventive hypotheses I read about was a merger in a triple star system. So Eta Car A and Eta Car B have a binary system now, but what if there was an Eta Car C that was orbiting around this and actually came in and got caught up and merged with Eta Car A? And they show that that could possibly provide the energy that produces the Great Eruption. Now, unfortunately, when there's evidence that there were also eruptions in 1550 and in around 1250, this merger hypothesis is a little sketchy because, well, what happened at those times, right? I don't know. As I say, I'm not an expert in the Eta Car research. I really enjoy reading about it, but I can safely say that this is an active research topic. So what I am expert in is astronomy visualization. And I'm the lead on the AstroViz project that is part of NASA's Universe of Learning. Universe of Learning is a collaboration among 4 institutions: the Space Telescope Science Institute, Caltech IPAC, the Jet Propulsion Laboratory, and the Center for Astrophysics, Harvard and Smithsonian. And the AstroViz project has as its goal to create visualizations of astronomical things using multi-wavelength data from NASA in order to present learning messages to the public. All right, and as you can see here, we have done the Orion Nebula in visible and infrared light. We have done the Whirlpool Galaxy in infrared, visible, and X-ray. We have done visible, infrared, and X-ray of the Crab Nebula. And we've also released the video going through the ultra deep field. So we have done these large-scale cinematic visualization projects. And for last year, we chose to do Eta Carinae. So here's how we went about creating some of this model. Now, first of all, there is pre-existing models of the Homunculus Nebula. Researchers have been looking at this for decades and decades. So, of course, they have ideas. And it's basically, two big bubbles, right? It's an hourglass shape. And so this was the latest model that came out in somewhere around 2015, 2016 timeframe from my friend Wolfgang Steffen, working with a bunch of collaborators, scientific collaborators. And they got the basics of it based upon some velocity information about it. And there were, unfortunately, two things I didn't like about this model for use in our things. The first thing is that these protrusions here, okay, are supposed to match these protrusions here in the dust skirt, what I call the equatorial emission. And one of their results was that these protrusions were tilted, that this one was going away from us and this one was coming towards us. And when we talked with our expert and looked at the 3D modeling of it, and particularly also when we were using the ultraviolet, it didn't seem to work. So we changed it and we put those in the equatorial plane. The second thing we didn't like about it is that it's orange. The Homunculus Nebula is an orange. And so the most important thing we did in improving their model was to create the surface texture. And so here is some of the texture development we did. This was done by one of our amazing artists, Danny Player. And you can see it started out looking somewhat like a paper lantern. It was a very thin layer going through. And she had lots of small scale noise. We use something called noise in computer graphics to create these random patterns to try and, replicate or not exactly replicate, but mimic the look and feel of the Eta Car. And then she added in lots of larger scale noise and, dialed it back a bit until we get to our final view, which is like this. So creating the bulbs of the Homunculus Nebula and getting that surface texture to look and feel like the actual Homunculus Nebula. Here is actually the final, which comes out of the composite. We render things and we go into a compositing program where we can adjust colors, we can brighten and highlight and work on this so we can adjust it after we've already rendered the 3D model. And if you turn this sideways, you can see here are the protrusions that we put in the equatorial plane. I also asked Danny to put in a third protrusion just for sort of symmetry in 3D. When we spun this around in 3D and we just used those two protrusions, it felt kind of lopsided. So I took artistic license and we added a protrusion that actually goes out the back. So we can't see it from Earth. So if it exists, great. It probably doesn't exist, but just for the 3D look and feel, we added it for artistic purposes. Then we go on to the ultraviolet. All right, and as we talked about previously in the ultraviolet, that we have the equatorial spikes here. We have the spikes that come out the tops of the lobes, and then there's just a little bit of haze that works around there. All right, and then you composite that on top of the Homunculus Nebula as done in visible light. So there is no ultraviolet light model. It's really the visible light model and then the ultraviolet light added on top of it. So we're building layer upon layer in this model. Hydrogen alpha, again, it's all this cloudy stuff that's further out, and we had to correlate with the ultraviolet. Here's the hydrogen alpha render. Oh, you'll also notice that these renders are in black and white. That's because the color actually gets added in the composite. There's no need to add color in the render. We can just do all that when we do the comp. All right, and so here is the hydrogen alpha, multi-layered, adjusted, smooth, put on top of that. And then we do the X-rays. I'm going to blew up the X-ray light model here, so you can see another feature of our modeling is that this is the visible light homunculus nebula here. And when we render the outer layers, we need to put that in as a solid black object, okay? Call it a 3D matte, so that the light that would be on the far side of the homunculus doesn't appear in the render. So as we're rotating around it, that will block all the light from the far side and only the flat light that you can see. All right, and so here is the X-ray model, and then the composite onto all of this, where we get the full thing. So here are the 3D model layers, the homunculus, adding the ultraviolet, adding the H-alpha, and adding the X-ray to give us this full multi-wavelength view of these really cool structures. Still, there's one more wavelength, that infrared, all right, which we wanted to show off how bright Eta Car is in the infrared. So this is the Spitzer image, and you'll notice it's got a ton of stars. And what we really want to model is the nebula here. There will be stars, but we got to get rid of those. And so, boom, there you go. Goodbye, stars. That's a tremendous amount of Photoshop work done by one of our artists, probably Elisa Pagan. Just amazing stuff to get rid of all those stars and leave us with this surface of the nebula. We then take that surface of the nebula and we analyze it for its 3D structure. What stuff is furthest away from us? What stuff is a little closer, and all the way further forward. So what we created here is what we call a decoupage model, a sculpted decoupage model. So here is Leah Hustak's analysis of this, working with myself and Robert Hurt to try and analyze which layers are where in 3D relation. And here is the 3D model with the camera representing the Earth viewpoint, and the layers all being these flat layers that are then sculpted into small shapes to produce the illusion of a full 3D model as the camera backs out. And you may think to yourself, well, come on, flat layers, that's not going to convince me. Yeah, you're wrong. It does convince you. It's really, it's a technique that's much more effective than it really has any right to be. Okay, so now we get to our movie. Okay, and the movie is Eta Carinae, the Great Eruption of a Massive Star. And I put the wonderful visualization team, Joe Olmsted, who did the ultraviolet, the hydrogen alpha, and the X-ray layers, Danny Player, who did the homunculus layer, Leah Hostak, who did compositing, the infrared, Elisa Pagan and Joe Pasquale, who did the 2D image processing, Greg Bacon, who's the producer, myself, and Robert Hurt, who worked on the infrared. I can't thank them enough. Don't give me all the credit. I was just the director of all this. They did most of the hard work. And I also have to thank our funding agent from NASA's Universal Learning. And because we are Universal Learning, this is not an entertainment movie. This is a movie that's trying to, yes, it's trying to be cinematic and show you some really gorgeous stuff, but it's also trying to teach you a story. I don't want to say teach. I want to present you with a story so that you gain some knowledge while watching it. So you'll notice that it is not narrated, but instead it has the captions on screen that you can read. And people have asked me, well, why don't you just hire a narrator and do that? And so people don't have to read. And I say that, well, we are trying to put people in a learning mode. And when you read the text on screen, You have to sort of concentrate. You have to put yourself into it a little bit more than if you're just sitting back and watching something on YouTube or whatever streaming service you happen to be watching. We're not trying to do entertainment. We're trying to do focused and enjoyable and some focused learning. All right. So if you want to see this movie again, you can, of course, find it on our Hubble Space Telescope channel on YouTube, which the same channel that you're watching right now in order to watch this talk. All right. It is a 4.5 minute. It has a soundtrack and the text is on screen. So everybody, please enjoy our visualization movie. I hope you enjoyed our presentation. Every time I see it, it's like, okay, yeah, these guys did a fantastic job. But there's still more to learn about this, okay? So as part of Universal Learning, we also have a project that creates this website called Universe Unplugged. And in addition to these videos being posted on our Hubble site and our Hubble Space Telescope channel on YouTube, they're also posted here on Universe Unplugged. But what Universe Unplugged does is it provides a lot more resources to these videos. So also on the Universe Unplugged site are these related resources, such as these here from our ViewSpace project, also part of the Universe of Learning. And these resources here from the AstroPix project, yet another thing from Universal Learning, as well as stuff from our Hubble site website and the Worldwide Telescope. So lots more to explore if you're interested in exploring more. You can also find on Universe Unplugged accessible learning resources. Robert Hurt took our 3D model of the homunculus and worked it out into a 3D printable object. And here you can see the 3D print of our Eta Car model. So you have a tactile, touchable thing that you can hold and examine it and understand. And Kim Arcand up at the Center for Astrophysics took our visualization and used it in her sonification project, Universe of Sound. And a link to that is, as I said, available on the Universe Unplugged website. So through the Universe of Learning, we've got various ways of exploring it. We take our base product of the Eta Car visualization and use it in multiple ways. It also served as an impetus for this year's NASA's Astrophoto Challenges. These Astrophoto Challenges are ways that you can try your hand at processing or capturing images. And the 2022 challenges, as you can see here, are Eta Car and the Carinae Nebula. There is a NASA data challenge, which provides data taken by several NASA telescopes, and you can figure out how you want to put together the version of an image. Or there is the Micro Observatory Challenge, where you get to actually observe using a robotic telescope. You don't get to go to the telescope and sit on the mountaintop and do it. But over the internet, you can use a robotic telescope to take observations, and then with those observations, you can process your own image. This NASA's Astrophoto Challenge just opened yesterday. And is now open through the summer. Submissions are due on July 31st. And finally, one of the things that is coming soon, actually in 2 weeks, is Dome/VR version of our visualization. So I don't have a dome here in my basement. I don't work at a planetarium. I can't use a dome. So what I actually do is, here's a picture of me sitting in my office pre-pandemic, back when I was still in my office, utilizing VR goggles to create a virtual dome around me. So I can spin around and look and see what the visualization looks like in a dome setting. That allows me to create a dome version. This is a frame from one of the dome versions that will debut at the Middle Atlantic Planetarium Society Conference in mid-May, basically 2 weeks from when I'm giving this talk. All right, so that is our exploration of Eta Carinae and the Homunculus Nebula in 3D. You can see that we explore it in its multi-wavelength glory. We can produce multi-formats in terms of the movies and the domes, and we even give you multi-sensory experiences with the 3D models and the sonification. So as I like to say, it's a multi-wavelength, multi-format, multi-sensory experience of one of this night sky's coolest, most interesting cosmic objects. Thank you all for your attention tonight. All right. So I have finished my talk. And at this point, I would usually take the host privilege of asking the first question, but that would be kind of weird. So Grant has jumped on very quickly. Grant, you've been monitoring the chat. Do we have some questions from the chat today?
We do. We have a solid online audience today. So to start off with, it is a question that we get often, but I'm going to have to ask you again. What is the difference between your visualizations and an artist's rendition?
All right. So our scientific visualizations are based on scientific knowledge, right? You can see that we utilize the scientific model created by Stefan et al. As the basis for our homunculus model. We use the data from Hubble and from Chandra as the basis for our 3D visualizations. We are trying to be scientifically accurate as reasonable for our cinematic level of visualization. I will say, however, that we are not trying to be perfectly scientifically accurate. To do so would be, well, certainly impossible for things like the infrared pullout, where we had to have thousands of stars and we could never figure out all the distances on them. But the idea is to give you a good mental model of the structures in 3D that you might see in these images. So you see a 2D flat image from NASA. How do you interpret that in 3D? One of the most important things I can do for you is give you that mental model with which you can then interpret that image. And that's not something you will find from an animation. Animations are generally drawn from the artist's head. They don't. They can use materials to inspire them, but they're not constrained by trying to get the science ideas right and get the correct messages across. They're just oftentimes trying to make something beautiful or something spectacular or something exciting. And so this is constrained by the science for our visualizations.
Awesome. Thank you. We actually have someone in the chat who worked on it at Goddard Space Flight Center. She says they created the model from the molecular hydrogen emissions that were extracted from ESO and X-shooter observations.
Yes.
All right. So we'll move on to our next question here. All right. So when we were actually talking about Eta Carinae itself, you had the visualization up. Is the equatorial plane of the nebula also the orbital plane of the binary system?
That I do not know, and I'm not sure anybody knows that. Okay, I looked to try and see if that I could find a paper that said definitively yes or no. I did not find one. However, if there is this colliding wind binary system and there is an axis, it would be a good hypothesis that the plane of the plane of the orbit would be the same as the equatorial plane of the system. Why did the material flow out in two opposite directions? Okay, what is there that creates that thing? I had originally thought that there was some dust disk or heavy material that's stopping it, that's collimating the flow out. And Chris Davidson said, no, that's not what's happening. It actually did blow off into direction. It's like, okay, I have a hard time as a non-specialist imagining why that would happen. You've got to have some reason for the bipolar symmetry.
Okay, thank you. Also, would you give a little more insight onto like what types of programs you use? Or I mean, no, we have a whole special about this to this user, Frank, and one of our resident artists actually did a whole talk about this, what the different colors mean, all of that. I would highly suggest you guys check out that public talk, but for the sake of this one, for a condensed answer.
All right, so in terms of the software we use anything that does the job. Okay, a lot of the time when I am taking the raw scientific data and turning it into data that I can use in a visualization, I'm writing Perl code, Perl scripts. I'm writing C code. I'm writing Fortran code. I'm doing whatever coding I can create to take the scientific data, pull it into things. Once we've got it into those packages, we use standard 3D modeling programs, and I'm actually not supposed to say which 3D modeling packages we use because we're NASA. We're not supposed to advertise for different companies. But I will say it's the same 3D modeling programs that Hollywood uses for these blockbuster films. Okay, Hollywood has put tremendous money into creating 3D modeling programs that do amazing things, and 90% of it we wouldn't use for science. But since they've created such great things, especially their camera choreography, oh my God, I love the camera choreography tools that they've written. We use that. We also use your image processing programs that take your images and change them. We use the compositing programs that also Hollywood uses. We've diversified into using lots of different ones. And so, as I said, we sort of will use whatever tool is necessary to get things out. We really could not have done this if we weren't able to sponge off of Hollywood and the investment that companies have made to sell their products to Hollywood, so that we can use, a small percentage of that stuff, but have really sophisticated tools and use them for science.
Awesome. All right. So as far as Eta Car, where do you see this going in terms of scientific observation? What do you think would be the next study done on it?
Well, I would like to know where that fast ejecta is. Okay. Can they design a study in order to observe that fast ejecta? That's creating the X-rays on the outside. That was the one of the big questions, and I've got partial answer there on that. Most of the main research that's being done on Eta Car right now is really down in the binary system, trying to understand the energetics of what happens when it's at periastron, when it's at apastron, following the energetics of this, trying to figure out how the Great Eruption could have happened to produce this amazing thing, amazing amount of energy production from it. So they're going to continue doing that. I was talking with one of the researchers last week. He said he was like, "Oh man, you should have done this project, a year from now, because we got some really good papers coming out this summer that you'll be able to use and really show even more what's going on." And so I find that happens a lot. That we did the Crab Nebula, right?
You're saying there's a part 2.
Well, I don't know. In terms of what we were doing, we're doing the big structures in 3D so that we can give the public a feel of that. I think his papers are going to be about the core energy that's going on in there, and we'll understand it a bit more. But it's not really going to change the 3D structure that we visualized in this one. And with all apologies to the researchers who do this, the public doesn't truly care about all these tiny details, or at least it's very hard to get them interested in all these tiny details. Our audience here, yeah, we can go into a lot more detail, but there was only so much depth we could go into a 4.5-minute one when you're making it for the general public. There's all sorts of cool scientific research details. And we have to find the right forum upon which to find that audience that's interested in those.
All right, and kind of piggybacking off that, do we have any sort of approximate size or distance from the nebula's center to outer layers? Do we have any idea?
Okay, yeah. I sort of meant to mention this. I think my recollection is the size of each lobe is about 0.4 of a light year. Okay, that the stuff's been expanding at like 600 kilometers per second for 200 years. You do the math on that, you get about 0.4 of a light year in diameter for each of those. So approximately a little less than a light year across the entire Eta Car. And if one of the researchers is watching this, please correct me in the comments if I'm wrong on that. Okay.
Myron Teodoro, the person who worked on it, says 21,000 AU.
21,000 AU. Okay, which is
it's nice having an expert in the chat. This is great. Thank you, Mert.
Thank you.
All right. So, are there studies going on as to what stopped Eta Car from going all the way to supernova?
If you're trying to figure out what caused it to go with this great eruption, I think you got to figure out some way that, yeah, why does it stop? I mean, if it was a small scale supernova, right? Well, why didn't it go all the way? Was it an instant? And you know, my understanding is that Eta Car A is only 1 million years old. Okay, and yeah, these massive stars burn through their undergo nuclear fusion very, very fast, and they go through they fuse hydrogen at a really, really rapid pace. But you're not going to get a supernova while you're still in the hydrogen burning phase, and that was my understanding was it was still in the hydrogen burning phase. So I didn't see how you could get a small scale supernova type thing. So that was a little confusing to me. But you know, I know that the researchers will continue to look for that. So if you're going to get a runaway a fusion or whatever processes that runs away, it has to be a temporary runaway, but then it has to die out and come back. They say that you know, based upon internal structure arguments, that it should have recovered after about 40 years, but here we are only 180 years later, and it still hasn't fully recovered. So I think that sort of it speaks to how we only know so much about it, and we're still working on it.
All right. And the chat, I believe you have answered all of their questions.
Well, fantastic. Okay. All right, then. Well, thank you all for listening today. We will be back in June. Cameron Hummels will talk about the formation and evolution of galaxies. We will see you then. Thank you for listening.